They were here for work. Their mom was studying chemistry, so I told the kids to go out and play humans versus zombies. Figuring.
Oh, so it's your fault. Great.
Pretty much.
Thank you.
Well, I figured they would just run around, and I would have let them shoot me if I was a zombie and just
Did you give him your gun?
enjoyed. No.
No, because he had a big gun. He had
I know.
the ones that you have and that Zach has.
Yeah, he just was carrying it around. I don't think he even knew we were playing the game. He just literally carrying it around just to carry a Nerf gun around, which I got to admit, that's the only reason I play the game, is an excuse to carry the Nerf gun around. And to shoot Haley in the back.
That's not nice.
Well, come on, you're a pretty lazy-ass zombie.
I knew it too, right when the door opened, I was like, crap, today.
Yes. Okay, so let's start in, oh, I did turn the recorder on, didn't I?
Yes.
Yes, it is blinking. So let's start in on Chapter 7. What Chapter 7 is going to be is basically we're going to look at molecular compounds and the sharing of electrons. So that's going to be the hard part. Or really, I think that the sharing of them is actually reasonably easy. The hard part is just that sharing is more complicated than just gaining and losing electrons like normal molecules. So if we take a look and do a little bit of review, we talked about ionic compounds and molecular compounds. And we're going to keep coming back to this to basically mostly contrast them, not really compare them. And so ionic compounds, what we found is that they gain or lose electrons, right? And we've always said that one of the things that differentiates molecular compounds is that they share electrons. So let's take a look at why they gain and lose electrons versus, for instance, why they might want to share electrons. Now, we've already done the gaining or losing electrons for ionic compounds. We said, for instance, that if we're making, sodium plus fluorine, that's going to make sodium fluoride, and that we know that the sodium is +1 and the fluorine is -1, and we know that this is 1s2, 2s2, 2p6, 3s1. Oops, that's a 1. And we know for the fluorine is 1s2, 2s2, 2p6, 2p5. Whoops. And so the idea is that we take that one electron from the sodium and we give that electron to fluorine so that on the other side, both of them have completed octets and have a 1s2, 2s2, 2p6 electron configuration. And so that completing the octet is sort of the goal, or to basically have a filled outer shell. And the reason for that is, if you look at it, is that if we take an electron from the 1s, this is rather loosely held. And I know I spelled it loosely wrong, but that's okay. Loosely held because it's got all these inner shell electrons sort of shielding it from the nucleus. Whereas here we know that it's okay to accept an electron because we know that it can see the nucleus. And the idea is that, the nucleus is where the protons are, they're attracted to that. And so for ionic compounds, the net result is that we have simply an electrostatic attraction between the sodium and the fluorine, between the positive charge and the negative charge. Now, sharing electrons is a lot more complicated. For instance, if we take a look, we know that this happens. For instance, we never find fluorine by itself. We always find fluorine as a diatomic. So we know that that diatomic fluorine is very stable because that's its normal state. And so how can we explain that thinking about it in terms of electron orbitals? Well, if each fluorine is 1s2, 2s2, 2p5, they both want to gain an electron, right? And neither really wants to lose one. And so, if we really did gain and lose an electron, then we'd end up with one that's 1s2, 2s2, 2p6. He's happy. That would be the fluorine with an extra electron. If I had a fluorine positive, 1s2, 2s2, 2p4, he's not happy. So we can't just gain and lose electrons. And so the next best thing to gaining and losing electrons is sharing. So let's take a look at how that sharing works. And really what we're going to spend a good chunk of today's lecture on and the next couple days is looking at the details of the sharing. And we're going to have a couple different models or a couple different mental pictures that we use. We'll have the real picture, or at least as close as we're going to get to the real picture of sharing, and that's the most complicated model. And so we won't use it very often. We'll look at it, we'll understand that that's the background behind everything, and then we'll abstract it one layer and say, hey, we can model sharing with this simpler view and this simpler way to keep track of things, and we'd be much more productive that way. And so realize that we're going to present things in a bunch of different ways, and that each way sort of emphasizes an independent feature of things. So one way we can do that is by looking at those orbitals. So if again we have the 1s2, 2s2, 2p5, and I have a 1s2, 2s2, 2p5, so those, 5. So these are my fluorines. Well, what we can do is we can say, what if they share an electron between them? Meaning that they both kind of look like this, 2s2, 2p, 5.5. So the idea is that this guy sometimes gives that one an electron, and that one sometimes gives that one an electron. So it kind of averages out to maybe something like 2p, 5.5. Well, it's not perfect, but it's better than not sharing. So one way we can look at sharing is that the alternative is worse than the sharing part, that it's not perfect, but it's better than not sharing at all. And so we can kind of look at it like that. And that's kind of, this is a really rough picture, meaning it really doesn't work out to be 5.5. You really can't, do it in this way. But it's kind of a mental picture that you can have, which is that it's better to share than to not share. And so what we really want to look at is kind of what sharing truly is. And to do that, we have to kind of take a closer look at an atom. So one of the reasons I picked the McMurray book is some of the figures are really nice. Like I love figure 7.1 and 7.2. And so, I'm going to sketch them out here, but certainly you guys should make reference to them when you're kind of studying. And if you're in your notes, you can kind of sketch the picture and say, well, I can probably have a better picture if I go look in the book than the crappy one Jay can sketch. So the idea is that if I'm still looking at my fluorines, I've got a nucleus, right? So here's my positive charge, and then I've got another nucleus, and that's my positive charge. And then, I have my 1s orbital, and I've got a 1s orbital. And then, out here further, I've got my 2s orbitals. They're not exactly circular. They're not even the same size. Welcome to Jay's drawing skills. Now, what do we know about the nucleuses in here? What do we know about the forces between the nuclei? Yeah, this is a repulsive force. Because we know that positive and positive won't be attracted together. What do we know about, say, an electron here and the nucleus? Nathan? What do we know about electrons and nucleuses? Attraction, repulsion? Yeah, there's an attractive force, right? But not only is there an attractive force for the nucleus and its own electrons, another nucleus would also be attracted to that. And if I have an electron on this fluorine, that electron is also attracted to the opposite nucleus. And so what we've really got is sort of a balance that develops, where the attractive forces sort of are almost the same as the repulsive forces. And it's really the attractive force for a nucleus on one atom for the electrons in the other atom and vice versa that work. And so one of the things I like about this diagram is it shows us that there is repulsive forces, right? And that there are attractive forces holding it together. And so when we take a look at the next figure, figure 7.2, where it's abstracted, meaning it's not as obvious what's going on, to me at least, is that we can have sort of energy. And this is the distance between the hydrogen nuclei, or between the fluorine nucleus. Now, if you look in your book, they use hydrogen, and hydrogen's fine to use as an example. I don't like to use it as the example simply because it's the exact same one as the book, and also because hydrogen is a little simple in that it only has one electron, whereas fluorine's a little bit more complicated. It has more electrons. And what we find is that, you know, there's the zero energy level. And then, of course, we've got positive and negative. Notice we're not putting any values on this because we don't really care. And what happens is you get an energy curve that looks sort of like this, where here my fluorines are too close together, and there's that repulsive force forcing them apart. You've got out here where you have your two fluorine atoms too far apart, so there's no attractive force. And then you have right here sort of where if we kind of draw their orbitals like this, they actually overlap. That's not a lot of overlap. Let me have some more overlap between my orbitals. So you've got one that's overlapped like this. You've got another one that's like this. They've got that region in there where they actually basically share the electron. And so here we're in the region where the attractive force between the nucleus and the electron of the other atom leads to the attractive force being greater than the repulsive force. And so what you really end up having is sort of the optimal spot for those atoms to exist. I still didn't have a whole lot of overlap there. I should draw better pictures, but such is life. I'm not a very good artist. You can look at the picture in the book and see it much nicer. So the idea is that too close together is bad, too far apart is horrible. There is a middle ground at some distance between those atoms where the attractive forces are stronger than the repulsive forces, and it keeps those atoms stuck together. Another way to look at that is if I take a look at fluorine plus fluorine, so that reaction that I was drawing you, and then fluorine stuck together, what we're going to realize is that a dash represents those shared electrons. And so therefore it really represents two electrons because each fluorine is sharing one electron with the other fluorine. And so if we take a look at what happens energy-wise, in order to be attracted to each other, they have to release energy. So there's about, whoa, what's the value? I didn't write it down in my notes because that was silly. 159 kilojoules per mole. And then to break those apart, to pull them apart, that would be minus 159 kilojoules per mole. Thank you, Jess. Have a lovely afternoon. Study up for your Bio 111 test.
I gotta go with biology right now.
Yep. It's a tough day for some people. They get, well, my other chemistry class, since they're all pre-dental hygiene students, most of them also have a test tomorrow in anatomy and physiology over like 205 bones or how many ever bones there are in the body. I don't remember the exact number. Haley, are you texting over there?
Technically writing down the note.
Oh, cool. Technically. I like that. So, what?
No, it's like literally on the notes page.
Anyway, we're going to focus on this. So the idea is that 159 kilojoules per mole, that's representing that energy difference right there on our previous graph. So for fluorine, that's 159 kilojoules per mole. And I don't have in my notes, maybe I should add it, it doesn't matter. You can also figure out that optimal distance, meaning there's what we can consider a bond length, a specific distance between two fluorine nuclei that is optimal for that. And so we'll be talking about bond lengths kind of later on. So again, going back to our ionic versus, oops, I guess I need to leave more room, molecular. One of the other things that we said is these tend to form lattices, right? And these tend to form molecules. And the reason for that is we can have any number of positive and negative charges attracted to each other. Now, we'll find out that there's an optimal number, but that optimal number is more than 2, generally. Whereas molecules, we can only share electrons between 2 atoms. That just because of the way the geometry works, it's really impossible to share electrons between 3 atoms. It would be too complicated to do that. Now, you can't really draw a picture that shows why that is the case. Realize that if you do some complicated calculations, and maybe they're not even that complicated, but if you do some calculations that show how a 3-body system would work, it would be too fragile to really form very often. Now, there is a small little bit of chemistry that you can do where electrons might be shared between more than 2 atoms, but that's like the 0.01% of chemistry that we ignore, and we like to stick with the 99.99% of chemistry where that doesn't occur. Now, one of the other things that we pointed out is that ionic molecules generally have high melting points and boiling points, whereas molecules have low melting points and boiling points, and that these are generally hard and these are kind of softish. Yeah, that's the whole idea. So we're kind of going backwards and saying, okay, we told you this before and just said this is a general property. Now we can kind of explain some of this to you, as in we can add a layer of explanation. And what you'll find is in chemistry, that's a lot of times how things work. We always are going forward and then saying, oh yeah, and remember this new part that we're learning actually helps explain in more detail something previously that we've learned. And so we already know these things about ionic and molecular compounds. Now we can start to understand the why of it instead of just saying, well, Jay told us that ionic molecules form lattices and that molecular compounds are molecules that share electrons. Now we can know why they share electrons and why they don't, and why they do that. So if you take a look at it, one of the reasons for the high boiling points and high melting points is that lattice. So if you go back to chapter 6 and look up lattice energies, they're greater than usually 1,000 kilojoules per mole. Whereas if we take a look at molecules, remember that's the sharing of electrons, that bond energy is on the order of anywhere between 100 and say 500 kilojoules. So normally the attractive forces holding molecules together are weaker than the attractive forces holding ionic compounds together. And we'll even go into more detail later on in chapter 10, where we look at the concept of what are called intermolecular forces. And that's, for instance, if I have one water molecule, that represents the shared electrons. And then between those molecules, here, let me draw it a little bit more accurately. There's what we're going to call intermolecular forces, IMFs. And we're going to learn that these are generally much weaker than even shared electrons. And so that helps explain why those molecules have very low melting points and low boiling points. And so this idea of going to quantum mechanics, figuring out where the electrons are, understanding they're in these orbitals, thinking about the attractive and repulsive forces, gives us more insight to go back and hopefully understand kind of a little bit more about ionic compounds to begin with. Okay, so let's take a look at the sharing of electrons. So on one end of the spectrum, we're going to have ionic compounds, where our best example of that is maybe sodium chloride, where there's no sharing. And on the very far side, we can have what are called covalent molecules, where a good example of that would be hydrogen or fluorine, where both atoms are the same. This is where we have as close to perfect sharing as we can have. And so here's my black end of the spectrum. Here's the white. Realize that this middle ground, the gray area, is really where most of the molecules that we're going to talk about lay. They're not perfectly sharing the electrons. They're not not sharing, or they're not equally sharing the electrons either. And so this is where we call polar covalent. And what we have here is unequal sharing of electrons. And so that's where we have something like, say, HF, where the fluorine wants the electron more than the hydrogen. And so one of the ways that we can represent that is we can say that fluorine really has a little bit of a negative charge, and hydrogen has a little bit of a positive charge because of that unequal sharing. And so that little delta represents basically a small amount. And so what we're saying is that the molecule has a little bit of unequal sharing. So here, if we think about this, this is a perfect magnet, meaning one end is positive and one end is negative. If we take a look at, say, something like hydrogen, that's non-magnetic at all. There's not a positive end to that, and there's not a negative end to it. And if we take a look at HF, what we get is kind of like a weak magnet, meaning there's a partial positive end and a partial negative end. So this is strong, this is weak, or we can say partial, and this is none, basically. And so it's electrically symmetrical. If you look on page 227, they like to draw the diagrams like this. If we actually take a look at, say, sodium chloride, what we find is that if we look at the electron density around it, there's more electron density around the chlorine than there is around the sodium. So this is electron density. And again, this is where my picture is crappy looking. The picture in the book's got nice shaded colors and all sorts of fanciness. It almost looks three-dimensional. It's so pretty. If we take a look at HF, or the book uses HCl, we can use either one. Notice that there's an unequal sharing, but it's not as exaggerated. So this is, a partial negative here and a partial positive here. And if we take a look at, say, hydrogen, it's perfectly symmetrical molecule. Or if we take a look at fluorine, it's also perfectly symmetrical. So one of the things that's going to be important is being able to measure that sort of asymmetry when we're talking about those atoms. And the way we do that is through a measure, or something called electronegativity. And of course, I'm lazy. I will probably refer to that as EN from now on. Kind of makes sense, electronegativity, EN. And what this is it's the attractive force an atom has for the shared electrons in a bond. And so what that's saying is that, for instance, in this molecule for hydrogen fluoride, I was just going to put it on the previous page, but since we're on this page, fluorine has a high electronegativity, therefore it wants the electron more. And hydrogen has a low electronegativity, therefore it's not attracted, or it's not holding the electron close. And so in a tug of war between hydrogen and fluorine for that electron density, fluorine wins. Now, electronegativity is related to, but not the same, as both electron affinity and ionization energies. So that stood for electron, affinity, and ionization energy. And what it really is it's sort of a average of the two. So for instance, one of the things we knew is that fluorine has a very high electron affinity and has a very low ionization energy. Therefore, it has a high electronegativity. And hydrogen has basically a low electron affinity. It has a low ionization energy. Therefore, it has a low electronegativity. Don't worry too much about the interplay between those. It's not like it's 1-to-1. It's not like we statistically weight the average or anything weird like that. But it is kind of a combination of those. And so what that means is that on page, 228, and on the cheat sheet, you're given an electronegativity table. So you never have to memorize any of the things dealing with electronegativity. What I'm going to hold you responsible for is knowing how to use electronegativity and how to kind of interpret differences in electronegativity between things. So if we take a look at it, we can kind of make some statements. If we talk about the electronegativity across a row, we know that it increases. So what that means is that like alkali metals and stuff on the left side have low electronegativities, meaning they don't want electrons. Whereas, you know, the halogens, fluorine, chlorine, bromine, and iodine, they have a high electronegativity, therefore they want the electrons pretty much. It's supposed to be an electron. And if we take a look at it down a column, it decreases. So, you know, fluorine wants electrons, you know, it's much more than, say, bromine. Meaning that if I take a look at HF versus HBr, the electron density here is very exaggerated towards fluorine. For instance, in HBr, let's make a better picture. You know, there's going to be a slight exaggeration towards bromine, but not as much. And so here we can say that there's a high separation, or that if I'm taking a look at that magnet, that plus and that minus is fairly large. Whereas if I look at bromine, that difference between the small positive excess and the small negative excess is very small. So this is kind of a strong magnet. Stronger. This is sort of a weaker magnet. And so what we want to get used to for using electronegativity is kind of that conceptually we can figure out which molecules have bigger disparities or higher differences between the positive and the negative ends. We'd consider that to be more polar, and which molecules are sort of less polar in that. We also have a pretty simple definition that we can come up with. And this is sort of a black-white definition, meaning in the real world it's slightly more complicated than that. But essentially, if the difference in electronegativity between the elements is greater than 2.0, we say that that's mostly ionic. Therefore, they gain and lose electrons. If we say that the difference in electronegativity is less than 2.0, then they share the electrons, but it's unequal. And if the difference in electronegativity is exactly 0, meaning they have the exact same electronegativity, then they share the electrons equally. And so the idea is that this represents something that's ionic. This is what we were calling that polar covalent. And this is what we simply call covalent, meaning that it equally shares it. This is our full positive negative. This is partial positive, partial negative. And this really is no separation of charges. It's not a magnet at all, so I guess I'd kind of draw it as a magnet with no charges. Or if we're kind of looking at how we write things, this is how we would write NaCl, whereas if I wrote HF, I would say that there might be a partial positive and a partial negative charge. And this would be just my example of HH or FF, where there is no separation of charge. And so kind of have all these pictures stuck in your head. We've got the words ionic, polar, covalent, and covalent. We've also got the pictures where we write sodium chloride with full positive and negative charges. We write the polar covalent with those partial charges. And we write the total equal sharing. We don't show charges at all. We can also think about them as very strong magnets, like sodium chloride, very weak magnets, like the polar covalent molecules, or basically not behaving like magnets at all if it's simply a covalent molecule. So, for example, if I just randomly pick two elements, let's say barium chloride. So, if I want to calculate the difference in electronegativity, I have to go look up barium on the chart, which is 0.9. And I look up chlorine on the chart, which is 3.0. And so I'd say that that's 3.0 minus 0.9, that's 2.1. We conclude that this is really an ionic compound. But notice that if I do something similar, if I take, say, barium and I pair it up with, say, two bromine atoms, well, barium is still 0.9. Bromine on this chart is 2.8. So that's 2.8 minus 0.9. Boy, someone do the math. That would be 1.9. Is that right? 9 and 9, 18. Yeah, 1.9. Therefore, that really comes up as being polar covalent. So even though we normally think of this as an ionic molecule, or an ionic compound, I should say, where we really think about it as barium plus 2 and chlorines with a -1 charge, it really is in that gray area where it really is polar covalent, and maybe we should be saying that the barium has a partial positive and the chlorines really have partial negative charges. Now, we're not going to worry about that too much, meaning we'll still consider barium bromide an ionic compound because it really is a metal and a bunch of nonmetals. But we also have to realize that you can have ionic compounds that are really ionic, like sodium chloride or barium chloride, and you can have molecules that are less ionic and almost get to the point where they're not exactly sharing the electrons, but they're not exactly just giving them up either. So there's that big spectrum, and we try to stay with the black and the white definitions and realize that there's a whole lot of gray stuck between. Wow, that is an interesting set of lecture notes. It just says, here's some random stuff. So, how can we illustrate sharing? And our goal is that we want to have a simple model that's easy to use. And it turns out that someone has already come up with this model, and they call them Lewis structures. And of course, I don't remember what Lewis's first name is now off the top of my head. That's horrible. This is the same guy that we're going to come back to when we talk about acids and bases also. And what he realized through observation of many, many molecular compounds is he kind of realized that we have that octet rule. And we can use our knowledge about valence electrons. Do you guys remember what a valence electron is? It's kind of important here. Now, this is the number of electrons in the s and p outermost orbital. And what it is, you know, once we realize the trend and the pattern, valence electrons are very easy to calculate and do. At the beginning, maybe they're a little harder, but you'll find that you kind of memorize them. So one of the things we pointed out is, like, for instance, if I compare the lithium and the sodium row, the things they have in common is that's 1s2, 2s1. This is 1s2, 2s2, 2p6, 3s1. Notice that, what do they have in common? Yeah, one electron in the outermost shell, right? That's why they form +1 cations. Well, it also means that they have one valence electron, right? And that if we compare, say, fluorine and chlorine, oops, not the minuses, we're just looking at the neutral atoms. This is 1s2, 2s2, 2p5. This is 1s2, 2s2, 2p6, 3s2, 3p5. What's the same about these? They all have 7 electrons in the outermost orbitals. Therefore, they tend to form -1 anions because they want to gain an electron. But because they have 7 electrons in their outermost orbital, that means that they also have 7 valence electrons. And so if you look at it on the periodic table, it's pretty easy to see that that first column has 1 valence electron. The next column over, for instance, represented by beryllium, has 2 valence electrons. And then we've got a big gap for the d orbitals, right? And remember, what do we say about d orbitals? They're complicated, and we're going to try to ignore them, right? And so then we get to aluminum. Well, that's got 3 valence electrons. And the idea is that everything in that column has that many valence electrons. So if you could count from 1 to 8 on your fingers, you don't even have to take your shoes off, thankfully. You can figure out the valence electrons because you can just count over the number of column rows, right? And so if we keep going, we've got carbon, that's got 4. Nitrogen's got 5. Oxygen's got 6. Fluorine's got 7. And technically, if we throw in a noble gas, that's got 8 valence electrons. But again, we tend to ignore the noble gases because they don't react. They don't form anything, right? They don't bother sharing electrons because they're already happy. So what Lewis did is he said, I'm going to represent valence electrons as dots. So lithium has 1 dot. Beryllium has 2 dots. Aluminum gets 3 dots. Carbon gets how many? 4, right? Nitrogen's going to have 5. And here's where we have to realize that once we get to 5, we start pairing the dots up. Oxygen has 6. Fluorine has 7. And then again, we're going to ignore the neon. So the idea is that each dot represents a valence electron on the atom. Does that make sense? And so if I want to look at that, then what happens is if I take, say, for instance, a magnesium atom, that's got 2 valence electrons, right? Plus, say, an oxygen atom that's got 6 valence electrons. Well, we know that this is a metal, and this is a nonmetal. We know that if I wrote this out for magnesium, it would be something like 1s2, 2s2, 2p6, 3s2, like that. And oxygen would be 1s2, 2s2, 2p4. We know that for an ionic compound, if I write it using sort of this not garbage, but the showing where the electrons actually are in the orbitals, we end up with 2 atoms that have 1s2, 2s2, 2p6, and 1s2, 2s2, 2p6. But for Lewis structures, what we do is we simply show that magnesium lost 2 electrons. Oxygen has a full outer shell because it gained 2 electrons. And so instead of doing this 1s2, 2s2, 2p6 stuff, instead what Lewis structures allow us to do is just represent everything with dots. It makes life so much easier to keep track of dots than it is to keep track of the 1s2, 2s2, 2p6, 3s2. Hell, I'm tired of writing it. I'm tired of saying it. Dots are so much easier way to represent those valence electrons. And part of it is, honestly, I don't even care about the electrons in the lowest energy levels. Those are so close to the nucleus that they don't have any chemistry associated with them. They don't form bonds. They don't react with anything that, you know, we could really ignore them. And so really, all we have to do is keep track of those outermost electrons. Does that make sense? Now, one thing to note is that if we have ions, we put brackets around them. So brackets indicate that we gained or lost electrons. And notice that I don't show any electrons around magnesium, even though technically it has a bunch of electrons in it still, right? It still has 8 electrons in its outermost shell, but that's not its outermost shell. It really should have a 3s shell, right? And so the 3s shell is really empty. Whereas for oxygen, if I'm showing that, I really do show all the electrons in that with the brackets because I really added 2 electrons to the outermost shell. And so we treat cations and anions a little bit differently. If we're taking the electrons away and we go down one set of shells, then we don't bother showing that full set of shells, even though we know it's there. But if we're adding the electrons to get to a full set of shells, we generally show those added electrons. So if you take a look at it, we can represent ionic molecules like this. And the beauty of Lewis structures is that they explain molecular compounds a lot better. So for instance, we've been talking about fluorine plus fluorine a couple times. And if we take a look at fluorine, it has 7 valence electrons. And, you know, we were writing this as 1s2, 2s2, 2p5, plus 1s2, 2s2, 2p5. And then when we did it over here, we said it's 1s2, 2s2, 2p5.5, and I put it in brackets because that's kind of wrong. Meaning that since we're not gaining or losing electrons, we can't show the sharing of electrons using the valence shell model, kind of. Instead, the way we show sharing of electrons in the Lewis structures is we have a line. So these represent unshared electrons. A line represents 2 shared electrons. Sometimes in a book you'll actually see it drawn like this, where they just put the shared electrons equally between the atoms, and it's recognized that those are shared. Sometimes they'll even go so far as to kind of color code it and say that the electrons on one fluorine atom are solid circles and the electrons on the other fluorine atom, you know, might be open circles. And so the fact that these are between the 2 fluorines means that, again, those are the pair that's shared. We'll stick with the normal convention, which is simply showing shared ones as dashes, showing unshared ones as the actual dots in the electrons. So that's how we can form or represent sharing in electrons. So Lewis structures are nice because they make sharing obvious. And they also make keeping track of that octet rule pretty easy, in that if I take a look at this fluorine, it has 8 electrons that belong to it. And if I take a look at this other fluorine, it also has 8 electrons that belong to it, meaning it's very easy to just count dots, right? It's a lot easier than doing the 1s2, 2s2, 2p5. So again, one thing you should remember or learn kind of in chemistry is that we like to have a bunch of different ways or different models to explain things. And we pick the model that we want to use to explain things based on one of 2 things. We try to use the easiest model possible, or the least effort, and that gives us the most insight. And then if we need a more complicated model to explain something, we pull it out of the drawer and say, hey, look, we know the simple model is not 100% perfect. Here's some modifications we can make to that simple model that allow it to explain some other things, but it also does add some complications to things. So what we want to be good at, or kind of do, is we're going to have to be really good at drawing these Lewis dot structures. We're going to have to practice a lot to sort of talk about how to share electrons. So what we'll do is on Monday, we'll talk about drawing Lewis structures. On Tuesday, we'll have your test, or chapters 5 and 6. On Wednesday, we'll do more Lewis stuff, probably. And then on Thursday, there's an entire lab where you're going to draw Lewis structures, plus you're going to end up building, and we'll talk about how to do that on Monday or Wednesday, three-dimensional models of these, so that we can get a better understanding, kind of what these atoms and molecules generally look like. Because I think if you don't have a picture of this stuff in your head, if it's just, arbitrary things written on a piece of paper, that it's not a good idea, that, you're not really getting the big picture. And you have to realize that when we put things on paper, we are limiting ourselves to just 2 dimensions, right? We can try to sketch 3 dimensions on paper. It gets hard. And, we'll even show you a vain attempt at doing it. But in the end, 3 dimensions is the way to go. Todd and I were talking about technology the other day, and one of the things that would be really awesome, and I don't know if they can do this yet, but apparently someone told me that, in like Avengers, where he's like has 3-dimensional models and he's like moving them around and spinning it in space and stuff. You guys remember seeing the movie, right? Everyone has.
Wait, what movie?
Not Avengers movie.
It's a pretty common thing.
Yeah, the one with the Hulk. That's the Avengers, isn't it?
With all of them
With the Hulk and Thor, Iron Man. Even in the normal Iron Man movie, he's rotating 3-dimensional things, right? If we had one of those in chemistry where I could be like, bam, here's the real 3-dimensional model, that would be awesome. That would give us better insight into what we're looking at. I don't think we can have that. Honestly, even if I know the technology actually exists. Someone told me that that it's pretty much in its infant stage right now, but you can really project 3-dimensional images now. The only thing that doesn't exist is I doubt someone's written a program to allow us to generate 3-dimensional models of atoms quite yet. Plus, I'm guessing that it costs more than my budget does. But you never know. We might be in the next 10 or 15 years when your kids come home to do their homework, they might be like, opening up their computer or something, having it project a 3D image and showing how molecules react and things like that, which would make, I think, the learning process a little bit easier sometimes because you'd have a more concrete grasp on things. So that's it for today. I guess we forgot to mention Thursday, we're just going to have a kind of a work day to get caught up, ask homework questions, etc. And then, of course, Friday for this week, there's no class because Jay has to go to a meeting. I know that breaks your heart, right? But such is life.